Live from the North Carolina Museum of Natural Sciences in beautiful downtown Raleigh. It's the Science Cafe with your host, Chris Smith.
All right, let's get started. Hi, everybody. Oh, this is great. What a crowd we've got tonight. Thanks for coming out to the Science Cafe every Thursday night here at the Museum of Natural Sciences. My name is Chris. I'm your host for the Science Cafe every week, and this is fabulous. Look at all these incredible people here to dive into some astronomy and astrophysics stuff. How many of you are here to learn about black holes? Yeah, that's it. I hope it's everybody. If not, the other talks must be somewhere around town. I'm not sure. But yeah, thanks for coming out tonight. A few things that I want to throw out there first before we get started with the program. On your tables, there's a blue sheet of paper, and that blue piece of paper has information about a research study that the museum's participating in to help scientists learn more about events like these, like science cafes and other science events. At the end of tonight's program, once we're done with the presentation and the Q&A, we're going to pass out a very small survey. Should take you no more than about 5 minutes to fill out. If you've come to the Science Cafe before and filled it out, you don't have to do it again, I think. But if you haven't filled it out, we'd love for you to do that. It's a national survey. And, you know, hey, you're at a Science Cafe. Why not help us do some science, right? That's a fun thing to do. So that would be a great help. Announcement number 2. If you like the Science Cafes, you like what we do, next Thursday night, we'll be back here at 7 o'clock, but we won't be in the cafe. We'll be in the WRAL 3D Theater in the other museum building up a little further up Jones Street. We're going to be screening a documentary, The New Noose River, and we'll have special guests, a panel. It's going to be great stuff, a very important film about where, if you live in Wake County, you get your water. So that one's probably pretty important to you, I think. And next Thursday night, we'll have food and drinks available for sale over on the other side. So go ahead and mark your calendars for that one, too. Now, on to black holes. Let's talk about some astronomy and astrophysics. I know very little. Fortunately, we have somebody here who knows a whole lot, Dr. Katie Mack from North Carolina State University. You might know, give it up for Katie. You might know Katie as Astro Katie on Twitter. She has amassed some 350,000 Twitter followers. So if you don't follow Astro Katie, you should, because on a regular basis, you just get all kinds of great nuggets of astrophysical knowledge dropped in your Twitter timeline. And it's really cool stuff. You'll learn something new every single day, just about, I guarantee it. But I'll let Katie, caveat that if she needs to at all. And another exciting thing, because she knows a lot, I know very little, but right now, this very moment, I feel kind of special because Katie and I wore the same physics shoes. Look at this. They have, oh my gosh, I don't even know what half the stuff on them are. I just knew I was hosting a science cafe on astrophysics and thought, that's some fashion I need to have. So we're going to leave it up to Dr. Katie Mack to elucidate all of the mysteries of our shoes and even more in the universe. Put your hands together and welcome to the stage, Dr. Katie Mack.
Hello. Thank you all for coming out tonight. I'm really excited to be here. I'm really excited to talk about black holes and to talk about this picture that you see on the screens and how that came about. Just as a caveat, I had nothing to do with that project. I'm a theorist. I don't do stuff with data, so I didn't make that picture. I didn't have anything to do with making that picture, but I'm very excited about black holes. I'm very excited about what we're learning about them and how projects like that, like the project to take a picture of a black hole, can teach us about the universe, about black holes, about galaxies and relativity and all sorts of things like that. So I'm going to start with an origin story. Well, it's a scary night out there. I'm going to start with the beginning, how to make a black hole. So you start with a star. This is our star. This is the sun. The sun will not make a black hole. There are certain requirements for a star to make a black hole, and the sun doesn't meet those requirements. What the sun will do is eventually it will run out of fuel in its core. It's currently burning hydrogen into helium. It will run out of hydrogen at some point. It'll puff up. It will make the Earth a lot hotter. It'll swallow up Mercury, maybe Venus. It'll destroy all life on Earth in some, several billion years. Don't worry about that right now. After it does that, it'll blow off its outer layers. It'll make a beautiful planetary nebula of sort of this gas that's blown off the outer layers of the star. We see these things all the time. In the centers of these nebulae are little white dwarf stars, which are these very dense, dead stars that are sort of just cooling over many billions of years. That's what our sun will do, but the point is that it's not a black hole. Our sun will not become a black hole. It won't even explode in a particularly dramatic way. It'll just kind of slough off some outer layers and make a pretty nebula. But our sun is not the only type of star out there. There are stars that are smaller than our sun. There are stars that are bigger than our sun. Our sun is somewhere in the middle of the sort of stellar population in terms of mass and size. So if you have a star that is something like 8 times as massive as the sun, a little bit more than that maybe, then when it runs out of fuel, it can do something really dramatic. It can explode in a supernova, and it can make a different kind of beautiful nebula, supernova remnant. This picture here is the Crab Nebula. It's got a pulsar in the middle. A pulsar is a neutron star, which is an extremely dense, dead star. It's got a strong magnetic field. It's spinning around. It's creating jets of radiation, and it's blowing out all this gas in this nebula. That, however, is also not a black hole. But we're getting closer. A neutron star is a very, very dense object, and it's held up by a kind of quantum pressure. If you have more mass than that, if you have a star that's more massive than the kind of star that can make a neutron star when it blows up, then you can have a different kind of explosion. You still get a beautiful supernova remnant, but then the thing that's left over from that can collapse into a black hole. Basically, the way you get a black hole is you put so much mass together, you have such a heavy thing that it collapses under its own gravity, and no force known to nature can stop it from collapsing down to a point. So there we finally have something that can make a black hole. You need a really massive star. You need a star that's something like tens of times the mass of the sun. And there are stars out there that are that massive, and when they die, when they explode as supernovae, they can then collapse and become black holes. So what is a black hole? So to talk about what a black hole is, we have to start with a little lesson in general relativity. So you may have seen a picture like this before. This is a kind of analogy, a sort of representation of how Einstein taught us that gravity works. So the idea behind Einstein's general relativity is that gravity comes from not a sort of force between things in the way we think of it usually, but from the shape of space itself. So when you have a massive object, it curves space around it. You can imagine if you had a trampoline, you put a bowling ball in the middle of the trampoline, that's sort of curving the trampoline, and then if you try to roll something past the bowling ball, it'll sort of move in this curved path. And that's a two-dimensional analogy for a sort of three-dimensional space, but that's kind of how Einstein imagines gravity, that you have a massive object creates a sort of dent or a curvature in space, and then when things are trying to move past that object, they're trying to move in a straight line, but the space they're in is curved, and so they move in a curved path. And that's how you get things like orbits, and that's how you get things falling toward massive objects. So if you have a situation like this, where you have a massive object making a dent in space, and then there's a smaller object that's trying to move past it, it'll follow a curved path because it's moving through a curved space. And it turns out that that even works for light. If light is trying to move through a curved space, the light will also travel in a curved path because light will just follow the curve of the space it's in. So you can get light bending around massive objects also, and that's called gravitational lensing. And so anytime you have a curvature in space, it can alter how things move around in that space. And a black hole is a situation where you have a very extreme curvature. So you have some kind of curvature in space that's so extreme that something trying to move past it would at some point fall in. Basically, the idea is a black hole has so much mass in such a small space that there's a point where if you get too close to it, there's no way to avoid falling into the black hole. That's called the event horizon. That's the point of no return. It's just a distance from the central sort of core of the black hole, where if you get closer than that, you are never coming out again. So here's a diagram showing a depiction of a black hole. So the singularity is the point at the center that everything is falling toward. It's a point of theoretically infinite density in the center of the object. And then there's a region around it, out to the distance of the event horizon, where everything within that region has to go toward the singularity. It cannot go away from the singularity. The space is so curved that it can't climb out of that space. So the event horizon is the point of no return. And if you had something, let's say you have a black hole and you have like a laser pointer outside the black hole and you're shooting some light, the light will travel in a kind of curved path around that black hole because the black hole is bending space a lot. If you put the thing close enough to the black hole, the light curves so much it can actually go in a circle around the black hole, so you can have circular orbits of light, whereas trying to to go away, but it just keeps curving around because the space is so curved. And if you have your laser pointer inside the event horizon, then the light will go into the singularity. And no matter which direction you point the laser pointer, the light will fall into the singularity. Everything goes into the singularity once you're inside the event horizon. There is no way to escape going into the singularity. So, of course, if you encounter a black hole, you should avoid getting that close to it. But generally speaking, people think of black holes as these extremely scary objects because they have this point of no return, but we actually see black holes all over the universe, and they're not dangerous to us. As long as you don't get too close, a black hole acts like any other massive gravitating object. Things can orbit around it, it can bend the light around it, but it's not going to sort of suck you in from far away. So how do we find black holes in the universe? Well, we generally find them because they're really bright, which you might be surprised by because, as I said, light can't escape a black hole, so how could a black hole be bright? The reason that black holes are bright is because things are falling into them, and as they fall in, they heat up and they make a lot of radiation. So this is a map of some of the black holes in our galaxy. This is a map of X-ray radiation in our galaxy. So in this map, the sort of central point in the map is the center of the galaxy, and it's a projection so that the plane of the galaxy is sort of along the horizontal. We see a lot of X-ray sources in our galaxy that we think are black holes, and we think what's happening with those objects is that you have a black hole, and the black hole and a star are orbiting around each other. And the black hole used to be a star, but it went supernova, it collapsed on itself, it became a black hole. And if that star had a companion star, if there were two stars orbiting each other, then when one of them becomes a black hole, it can start consuming its binary partner, which is not a very nice thing to do. And the way that happens is it sort of pulls material off of the other star, and that material forms a disk around the black hole, an accretion disk is what we call it. And as that material is falling in toward the black hole, it's being pulled really strongly by the gravity of the black hole. And so the material is crashing into other material and it's heating up just by the friction of that violence of that whirlpool. It's kind of like if you see a whirlpool in water, things are sort of flowing around and everything gets kind of churned up, and you can see the whirlpool in the water even if you can't see the water because everything's sort of moving around a lot. And you get a similar thing with black holes. So many things are churning around in the vicinity of a black hole that they can actually heat up so much that they can emit X-ray radiation, which is something that only happens when these things are really, really hot. And so we see these things all the time. And sometimes in that churning, magnetic fields get sort of twisted around, and that can create jets of radiation that come out of the poles of the disk of the material. So this is a diagram of what it looks like for some kinds of black holes when they have accretion disks around them. There's a black hole in the middle somewhere that you can't see in this diagram, and then there's an accretion disk, this disk of material falling into the black hole, and then there's a big jet of radiation, of high energy particles and radiation shooting out either end, and that's not coming out of the black hole, that's coming out of the sort of tangled up magnetic fields in the disk of material falling in. The black hole in these cases is very, very small in these pictures, but the gravity of the black hole is driving all of this activity, which can make this really hot, bright source of radiation, and also these massive jets of material shooting out of that area. And we can see these jets out in the universe. Sometimes we see that galaxies have supermassive black holes in the centers. In fact, every reasonably large galaxy we see, we think has a supermassive black hole in the center. And when I say supermassive, I mean something like 1 million or billion times as massive as the sun. Now, those don't form just from the collapse of a giant star. There's a process where the star collapses, makes a black hole, and then over billions of years, more material falls in and makes the black hole more massive, and so on, until you have a supermassive black hole in the center of your galaxy. And those things can have these jets that stretch out far beyond the edge of the galaxy. This one is a jet that goes out 5,000 light years from the center of its galaxy. So that's a really large jet of material coming out of that very massive black hole. Now again, in these cases, the black hole itself can be fairly small. The black hole is this extremely sort of compact object in the sense that it's a whole lot of material in a very small space. And so the kind of edge of the black hole, the event horizon, doesn't necessarily take up very much space. This galaxy here is one called M87, and the event horizon of that black hole is somewhere around the size of like our solar system. So that seems big to us, but to a galaxy, that's a small space. And this thing is very far away as well. This galaxy is something like 55 million light years away. And so even though the black hole is very massive, it's about 6.5 billion times as massive as the sun, it's very, very small if we wanted to look at it. And we do want to look at this black hole. We really want to see what this looks like. And so we can do our best. We can kind of zoom in. We can use creative methods of observation to try to see it. And that's what the Event Horizon Telescope was designed to do. And just a few months ago, they put out this image of the black hole at the center of the galaxy M87. Now, I'm going to explain what this image is really showing us and why it's really, really, really cool. So the geometry here is complicated. The geometry is complicated because we're talking about curved space-time, and it gets complicated, it gets weird, light does very strange things. So this is a diagram of what's happening with this black hole. Basically, you have an accretion disk around the black hole. The accretion disk is making radiation, and you're looking at the black hole sort of from on an angle, in some kind of angle, and you can see the sort of close side of the accretion disk as you normally would, but you can also see the back of the accretion disk that would, if the black hole were an ordinary object, be hidden behind the black hole. The reason you can see the stuff behind the black hole is because the light is bending around the black hole, because the space is so curved that the light is bending around. I'm going to show a animation that shows a black hole with an accretion disk rotating to show you what it looks like when the light is being bent around the black hole. So in this animation, the red and black is the black hole, and the blue and white is the accretion disk. And at the moment, in this still frame, it's set up so that the accretion disk is sort of horizontal, and then there's the black hole. Okay, and even just sitting there like that, you can see that the disk, which you would expect to be just a horizontal line, it sort of extends above and below the black hole because the light is being curved up and curved around the black hole. But when it rotates, you'll be able to see this a little more clearly. So when you're looking down on the black hole, it looks just like you'd expect. There's a disk around the hole. But when it curves around, the light from behind the black hole gets stretched both above and below. And so you can see the light on the other side of the black hole. You can see the part of the disk that's directly behind the black hole. And then there's also a space where you don't see any light from the disk because the light that should come to you from that direction goes into the black hole. So I'll show you another diagram that can give you another idea of this. These are weird, sort of mind-bending concepts. So it takes a lot, at least for me, it took a lot of looking at lots of different kinds of pictures to sort of figure out in my mind what's going on with the geometry here. So here's a set of simulations of what it would look like to image a black hole with different angles of the accretion disk. So on the bottom row of these diagrams, it's looking down on the accretion disk. So the disk is horizontal. You're looking at it from above, for example, and you just see a sort of donut shape, and there's a hole in the middle. And on the top row, on the top left picture, the disk is exactly horizontal, and you're looking edge on. And even in that one, you do see the disk above and below the black hole because the light is bending around. And so the other pictures are different angles of that accretion disk. And what you can see with all of these pictures is there's a black part in the middle of the diagram. And that black part in the middle of the diagram is where the light should be coming to you from that direction, but all the light that should have been coming from that direction falls into the black hole instead. The black hole is curving space so much that some of the light that we would expect to see goes straight into the black hole and never comes out again. And so what we're seeing in these simulations is what it would look like to be able to see a black hole swallow light and not let that light come out. And if we look at a particular one of these simulations, we can compare it to the image that was taken by the telescope, and we see it matches pretty well. And so that's telling us something about the orientation of the disk of this black hole. And I just want to dwell a little bit more on this picture, because I think it's just amazingly cool. That dark part in the middle of that picture is where light is just being removed from the universe. Like, there is brightness all behind that black hole, but we're not seeing it because it's going into the black hole and never coming out again. A black hole is defined in some ways by the fact that there's a region where even light cannot escape it. Even light cannot come out of that region because basically what happens is that the gravity is so strong that light would have to go faster than the speed of light to get out. Just like you'd have to move really fast to get off of the Earth. The escape velocity of the Earth is something like 11.2 kilometers per second. The escape velocity from the event horizon of a black hole is the speed of light. So if you were closer than that, you'd have to go faster than the speed of light to escape, and that's not possible. So anytime light gets closer than that to a black hole, it cannot escape. A black hole is a region where even light cannot escape the gravity. And it's a region where the space is bent so much that the paths of light are redirected in strange ways. And so what we see in these pictures is we see that happening. We see a region of space where the gravity is so strong that light is removed from the universe entirely. It's taken into the center of this black hole and it doesn't come out again. This is the first time we've ever seen that. We've known that black holes are out there. We've been able to use theoretical arguments to talk about how that should happen, how relativity says that black holes should exist and that there should be this point of no return, this event horizon, but we've never seen it until now. And now we're seeing the event horizon. We're seeing the region where light cannot escape because we're seeing that darkness where the light has been pulled out of the universe, pulled into the center of the black hole. That just blows my mind every time I think about it. I think that's just an amazing achievement. It's also an amazing achievement in the sense of being very well predicted by the theory. So this is an image that was that appeared in one of the scientific papers by the Event Horizon Telescope team, where they compared the central image is a simulation of what the black hole shadow should look like. And the right-hand image in this picture is a blurred image of the simulation, and the left-hand image is what we actually saw. And the agreement is incredible. Like, they really knew what they were doing with these simulations. It was a really amazing achievement to have been able to do that simulation, which is hard because general relativity is very, very hard to do with computers. And they were able to make that simulation. They were able to show where all the light would go, and then they were able to take the picture and actually see that. And one more thing I wanted to point out about this picture is, in this picture, the event horizon is a little bit inside that dark region. The ring itself is a little bit larger than the event horizon because of how the sort of photons, how the light moves around in that space. And I just want to point out how small this thing looks from here. Okay, I mentioned that the event horizon is somewhere around the size of the solar system, and this is in something that is 55 million light years away. And so if you work out how large that thing would look on the sky, like how much of an angle it would subtend if you were, how big it would look from here, it's 42 micro arc seconds. That's the size of the ring. So a micro arc second is a millionth of an arc second. An arc second is a 60th of an arc minute, and an arc minute is a 60th of a degree. So for some context in that, the moon is about half a degree across on the sky. So if you imagine the full moon, it kind of looks like that maybe. And the size of the black hole as viewed from here is just unimaginably smaller than that. If you go out and look, at the moon, you'll be able to distinguish with your eye things that are about 0.02 degrees, like sort of maybe see craters of about that size. That's the sort of limit of the human eye, and that's based on the wavelength of light that you're seeing and how big your eye is. So if you want to see smaller things, if you want to see sort of more detail in terms of smaller angles on the sky, you need larger eyes, basically. And so we use telescopes to do that. This is a dish from the Very Large Array in New Mexico. That's me in that picture. These are very large dishes. They're about 25 meters across. And those things, when they look in radio light, they can see something like 13 arc seconds. Now remember, the black hole is 42 micro arc seconds. So a telescope like that doesn't come even close. Now the Very Large Array does something where they take a whole lot of telescopes and they point them all at the sky at the same time, and they can combine those images to make it as though they had a giant telescope that was, kilometers across. So that's one picture of the Square Kilometer Array. The Very Large Array. The Square Kilometer Array is a different telescope that's being built now. The Very Large Array, and me sitting in front of it, and in and they can move those telescopes around so they can make them sort of farther apart or closer together to do different kinds of astronomy. And so when they're compact like that, when they're sort of as close as they can get to one another, their limit is about 0.31 arc seconds. And when they're about as wide apart as they can be, the limit would be about 9,000 micro arc seconds. Again, we need to get to 42 micro arc seconds. This is 9,000, so we're still not close. So even an array, even an array that makes a sort of virtual telescope kilometers across is not getting close to the resolution you need to look at a black hole at the center of another galaxy. So what the Event Horizon Telescope people did is they took every telescope they could find that could look at millimeter light. Millimeter radiation is a kind of radio light, and they linked them all together virtually to make a giant telescope as large as the Earth. So the way that works is that you can take all the data from all these telescopes, do some fancy computer matching of the light coming in, and then you get the resolution you would have for a telescope as large across as the Earth, and then you finally get the kind of resolution you need to see a black hole in another galaxy, 20 microarc seconds. And the way it works basically is the light comes in from far away, and each of these telescopes records the light and the sort of waveform of the light and the time it happens, and then later on, you bring all the data together from all those different telescopes, and you line up the times of all of them, and you figure out what it would look like if all of those telescopes were seeing everything at exactly the same time and joining together as if they were one big telescope. It's a lot of work, and it's a lot of computation. It's a heck of a lot of data. So this is an image of imaging scientist Dr. Katie Bauman, who was one of the team who did the algorithmic work to put this picture together, standing there with some of the data from these telescopes. It took something like 5 petabytes of data to put all of this information together. And there was so much data that they couldn't send it over the internet. They had to put these disks on airplanes to bring all of the data in, because it would have taken years and years to get the data back by internet, especially because one of the telescopes, I don't know if you noticed, was at the South Pole, and the South Pole can only observe in southern winter, and planes can only fly in southern summer. So they had to take the data, wait for the seasons to change, put the data on a plane, and send it back. If they'd tried to send it through the sort of satellite internet that you get at the South Pole, I think they said it would have taken something like 25 years. You don't want to wait that long. These, I don't know how many petabytes are on those disks, but that's a sample of at least some of the data. I think they have a lot more that they're still processing for other purposes as well. They also took an image of the black hole at the center of our galaxy, which I'll talk about later, but that one didn't, it's not ready. This is a kind of cool figure. I'm just going to show it for a moment from one of the papers talking about the data analysis. This is different versions of that picture if you took out one of the telescopes. So each sort of column is removing the data from one of the telescopes and seeing how good the picture is. So you can see that the worst one of these is the one where you take out the telescope from Chile. But each of these telescopes contributes something to the final image, so that putting them all together, you get a much better picture than individually, or even if you just subtract one of the telescopes. It's really a big team effort of all of these telescopes that allow you to have the beautiful image that we get. And I'm just going to show it one more time, because I just think it's really, really amazing. So that's the picture of a black hole. That's the shadow of the black hole. That's an image of what the event horizon is doing to the light in the vicinity of the black hole. So what's next for the Event Horizon Telescope? Now that they've taken a picture of a black hole in another galaxy, what are they going to do next? Well, one thing to do is to look at the supermassive black hole that we have nearby. So this is a drawing of our galaxy. So we're somewhere over there. The black hole is there. We have a supermassive black hole in the center of our galaxy. It's about 4 million times as massive as the sun, and we call it Sagittarius A star. It's a complicated historical reason why we call it that. It's A asterisk, not a star. But we know that it's there, and one of the reasons we know that it's there is that we can zoom into the center of the galaxy and look at stars orbiting very, very close to the center of the galaxy. And when you watch them over several years, they seem to be orbiting something very small and very dark. So here's an animation of some of those stars moving around in the center of the galaxy, and you can see some of them kind of like whipping around something that doesn't show up as a bright spot. I'm going to show that animation again. So as we watch these stars moving around in the center of the galaxy, we can see that there's something small and dark and very, very massive that all these stars are kind of whipping around over the course of many years. And it turns out when we calculate how big the event horizon of that black hole should be, it's a little bigger than it's not bigger, it's the angular size is bigger than the one in M87. So our black hole is much less massive than the M87 black hole. Our black hole is 4 million times as massive as the sun. The one in M87 is 6.5 billion times as massive as the sun. But our black hole is a lot closer. So this one is something like 26,000 light years away. The one in M87 is 55 million light years away. So if you work it out, our black hole's event horizon should look a little bigger. But there's a problem with imaging our black hole, which is that because our black hole is so much smaller, the stuff moving around it sort of makes it vary on much smaller timescales. So this is an infrared image of the sort of stars and the light around the central object in our galaxy. And if you watch it, it kind of flickers a little bit. So in the infrared, we can see that flickering, and that flickering is just kind of stuff around the black hole, stuff in the accretion disk flaring up a little bit, stuff maybe falling into the black hole and having a flare up on the accretion disk. And that fluctuation happens on pretty short time scales. Because it's kind of a small object, things can get around it pretty fast. And that fluctuation can happen over the course of hours. And because you need to add up the images from all these telescopes over the course of a night, if something is changing on the timescale of hours, it's going to be really hard to match up all of the images from all these different telescopes. So it's going to be really hard to make a virtual single dish telescope with telescopes in different parts of the Earth if the source is fluctuating a whole lot. So that's the difficulty with looking at our local supermassive black hole, is that it's a little bit too active. But a caveat is that when we do get really good images of it, we're going to have a movie. So it's not just going to be a picture. We're going to see a lot about how that fluctuation is happening and what's going on there. So how else to see them? I'm just going to go sort of quickly through this bit. One way we see black holes is how they bend the space around them. This is a simulation of a black hole moving across a star field, and you can see how it's distorting the space and it's making the light sort of bend around it. And it makes these kind of arcs of light as it moves past these stars in the background. That's called gravitational lensing. And we can see a lot of really interesting things with gravitational lensing. When we look at gravitational lensing done by a cluster of galaxies, for example, we can see arcs from galaxies far behind that cluster of galaxies. So this picture is a galaxy, a little blue galaxy that's right behind the cluster of galaxies you see in the center, but its light is being bent around by the curved space, and so you see it as a sort of arc on one side and then a little blip on the other side because the light is being bent and distorted in this really weird way. So if we were able to see that distortion by, for example, two black holes orbiting around each other, then it would look something like this. Now this is just a simulation. We can't see stuff like this, but this is how black holes distort the space around them and make the sort of light bend around. What we do see when it comes to black holes orbiting around each other is we can detect the way that the space is sort of wobbling around the edges there. So you see when the black holes are orbiting around each other, it sort of makes the space wobble, and we can see that with something called the LIGO Observatory. So this is the Laser Interferometry Gravitational Wave Observatory. If you're interested in hearing more about this thing and what it can do and how it can see black holes colliding with each other by how they wobble space-time around, I gave a Science Cafe talk about this in 2017, and I think it's probably still on the website. So check that out or ask me about it later. But that's one way we can do that. And as of now, the LIGO Observatory has seen many, many mergers of black holes through the effect they have on space. Not the bending of light, but the curving of space itself and the ripples that makes in space. And we can pick up those ripples in space, and we can sort of feel the space quakes from black holes colliding with each other. And we've detected many, many black hole collisions with the LIGO Observatory. We've even seen some neutron stars colliding with each other that probably then make black holes when they collide. And so it's been a very exciting time. So I think I'm out of time now. So I'll end there, but if you have questions, we're going to take questions for quite a while. And one of the things that the description of this talk mentioned that I didn't really put into the talk was stuff about how black holes connect with the end of the universe. I can answer some questions about that if you like, but I can also answer other questions you have about black holes, and just stick around. Thanks.
Let's give Dr. Mack a round of applause. Holy cow. Are y'all's minds blown like mine? Golly. All right. So, yeah, we're going to move into Q&A. We got some time left tonight. The way the Q&A works, since we got a large crowd here, I've got a microphone, and then my colleague Cindy over here has a microphone. So you wave at us, we'll bring you a microphone. Be patient with us. We got a lot of room to cover. If you are sitting in the overflow room and you've got questions, one of my colleagues, Katie, is in there. I'm just going to look at the camera. One of my colleagues, Katie, is there, and she's going to send questions to us. We're going to try to get to as many as we possibly can, and I think the first one is closest to me. So hands up again so we can kind of start spotting you, and every now and then flag us down.
I've always heard it said that if you could go in through a black hole, that you could actually go back or maybe go forward in time. What do you know about that?
Okay, so the first thing I'll say is it's a very bad idea to go into a black hole. For a number of reasons. One of them is that as you enter the black hole, you will be ripped apart because the gravity on your feet will be so much stronger than the gravity on your head that you'll be stretched out into spaghetti as you enter the black hole. This is something that we call spaghettification. That is actually the technical term for this process, spaghettification. So it's not a good idea to try it. In terms of what happens inside the black hole, we have theories about that, but we don't know for sure because we can't get any information out of the black hole. Because as far as we know, everything that goes into the black hole goes straight to the singularity, is destroyed, and we can't get data back if we throw something in. So we don't know for sure what happens in there, but it seems probable that what happens is you just get crushed at the center. There are sort of ideas about how you could have some kind of portal to some other realm, but as far as we can tell, black holes just form when stars collapse, and all that's in there is the singularity where everything is crushed and nothing exciting happens. But again, we don't really know for sure. There could be all sorts of weird quantum mechanical things that go on, and there are lots of really exciting discussions in theoretical physics right now about what thinking about that process can tell us about theoretical physics, about how quantum mechanics and gravity work. So it's a big open question, really.
What would happen if a black hole and neutron star met?
What would happen if black hole and neutron star met? It would go badly for the neutron star. That is one of the things that the LIGO Observatory is trying to see, is collisions between black holes and neutron stars. So we've definitely seen collisions between black holes. We've seen at least one collision between neutron stars. Last night, there was an announcement that that LIGO might have seen a collision between a black hole and a neutron star. It was a sort of preliminary event. Unfortunately, it was retracted, so it looks like we have not definitively seen that happen yet, but we very much expect that the LIGO Observatory will detect some of those collisions. And what will happen is that the neutron star will get torn apart as it's falling into the black hole, and then the black hole will become more massive.
Do black holes die, or do they have everlasting life?
Great question. So we think that black holes evaporate over time. So if you take a black hole and you leave it alone long enough, then some kind of weird quantum processes will happen where a little bit of radiation will kind of leak off the edges of the black hole. And that radiation, as it leaks off, carries away some of the mass of the black hole. So the black hole will sort of shrink in mass over time through that process, and will eventually get brighter and hotter and then disappear completely. That's a process called Hawking evaporation. Now, we don't know for sure if that happens because we've never been able to observe that. All the black holes that we know about are very massive, so things are falling into them. They're not sitting there decaying. But if you had a black hole that you left alone long enough, we think that this would happen. Or if you had a really small black hole, then it could radiate in that way. But all the astrophysical black holes we know about them because things are falling into them. So those are not black holes that are getting less massive, those are just getting more and more massive. But we do think that they will disappear eventually.
You said that our sun will never be a black hole, it's too small.
Yeah.
You said it will just burst slowly, which would be like emitting more and more heat until it bursts. Is that what's happening now?
So
global warming.
So the changes that the sun goes through are on timescales of millions or billions of years. The temperature of the sun, from our perspective, hasn't changed in any noticeable way over the course of human history, as far as we can tell. But if you waited a million, 100 million years or billion years, then the temperature at Earth would go up from the fact that the sun is burning more and more fuel, and it's going to have to burn hotter and hotter as it gets low on fuel, and then it'll sort of puff out and it'll affect the planets. But what's going on the Earth right now has a lot to do with the atmosphere and is not connected to what's going on with the sun.
I've got one for you.
Okay.
Liam, age 10, wants to know, when you were talking about the star disappearing, didn't you actually mean that the star is being destroyed or evaporated?
Which, I'm not sure which star.
I'll try another one.
Okay. Sorry.
Sorry, Liam. Do you like the movie Event Horizon?
Oh, I haven't seen the movie Event Horizon. That's terrible for me to admit. I haven't seen it. But the movie Interstellar has a nice visual depiction of a black hole in that movie. So you might have noticed some similarities between some of the black hole shadow pictures that I showed and the black hole that appears in the movie Event Horizon. They did a lot of really detailed physics calculations to get that picture of the black hole in the Interstellar movie looking about right. So, and they did some other cool stuff with relativity in that movie.
Are there multiple copies of the raw data and the output of the algorithm? Are they backed up?
Oh, the data from the Event Horizon Telescope? I assume they have lots of backups. I don't know. I don't know what they do with all that data because it's 5 petabytes, so it's very expensive to hold on to all that data. But I assume they have at least one backup for each telescope. I just don't know. I don't know the details of that because I haven't been involved in it.
So when matter gets into a black hole, does it like get squished into quarks, or like how does it just all like?
Yeah, so we really don't know. All we know is that once you get to that kind of extreme gravity, no kind of force of nature that we know of can keep things from collapsing. So whatever happens to the stuff inside, it's about as destroyed as anything could possibly be. But we don't know what sort of that process looks like because we can't see into it. But you can kind of like, at the point the black hole exists, you can kind of think of that matter as not really existing anymore because it's inaccessible to us because it's behind this event horizon, so we can't learn anything about it. So you can sort of just think of black holes as just pure space-time curvature. Like all they are is this dent in space-time, this sort of defect in the fabric of space that persists because it's sort of already there. It sort of stays there with its own gravity.
What would you observe if happening to someone if you pushed them into the event horizon of a black hole?
That would be really mean.
But besides that,
yeah. So if you were standing back and you saw someone accidentally fall into a black hole, you would never see them cross the event horizon, because once they're past the event horizon, none of the light, no information from them can get to you. What you would see is you would see this sort of slow motion falling, and then they'd appear to be kind of frozen at the event horizon, then they'd just fade away. They'd get very red, very dark, and just fade away. So the light that's coming from them as they get closer to the event horizon is having to climb out of this gravitational well, and so it's losing energy as the light is trying to leave that person. And so the light gets redder because it's being sort of stretched out, and that makes light redder. And they would appear to slow down because when you're in a very strong gravitational field, your time is going more slowly compared to people outside that gravitational field. So they would appear to be kind of slowing down and freezing and then fading away. What would actually happen to them is as they cross the event horizon, they probably wouldn't notice when that happens. So, I mean, they'll be in the process of being kind of ripped apart as they're falling in. But the event horizon itself, at that border, probably doesn't have any especially strong effect on them during that process of falling in. There's still some big arguments in the physics community about how true that is, because there's this whole thing about what kind of quantum mechanical processes might happen at the event horizon, and that's a whole other discussion. But probably in terms of if you take relativity seriously, they wouldn't feel anything particularly different. They don't notice their time is slowing down. They would see everybody else kind of speeding up, but you know, I mean, but then they'd die, so that would be sad.
So much of what you've said depends on nothing being able to go faster than light. I'm wondering why the speed of light is a constant. Why can't light or something else be injected with enough energy so that it would go faster and maybe then could escape a black hole?
So as far as we know, the speed of light is an absolute speed limit in the universe. As far as we know, nothing can travel faster than the speed of light. This is part of the theory of relativity. And every experiment we've done, every piece of data we have is consistent with the idea that the speed of light is an absolute limit. It's the only speed light can travel if it's going through a vacuum. And it also appears to be the speed of gravitational waves. So we've been able to measure these gravitational waves, these ripples in space from black holes colliding. We've been able to measure how fast those are traveling, and those travel at the speed of light as well. And in fact, I think that we actually have measured the speed of gravity with more precision than the speed of light, but it's the same number. So that seems to be the speed at which both light and gravity travel through the vacuum of space. We've never seen anything inconsistent with that. So it appears that that's just how the universe works. So that there's definitely part of relativity. It has to do with causality. That has to do with sort of how time is structured. Yeah, weird things would happen if that limit could be broken. But as far as we know, it just seems to be the law of the universe. So the question was, is it theoretically acceptable that it's constant? Yeah, it's part of the theory. It's built into the theory of relativity that the speed of light is constant and that you can't go faster than it. But experimentally it seems to hold up extremely well. So. Yeah.
What factors determine the orientation of the disk?
Sorry.
I'm over here.
Oh, okay. What factors determine? The disk around the black hole. Just how in what direction the matter was already traveling. So in general, in space, if you have gas, that's bound in some kind of gravitational way, it'll form a disk. So there's a disk, our solar system is a disk because we had this protoplanetary disk of material around our star. Galaxies tend to form disks, and matter falling into black holes tends to form disk. And that's just because of how, like, if there's a little bit of sort of bulk rotation in the material to begin with, then that'll be kind of flattened out. The same way that if you take a bit of dough and you spin it in the air and it flattens out to a pizza, you get sort of a similar process with gas in the universe that's being held together, held in by gravity. Things tend to form disks, and it has to do with angular momentum and stuff like that. And I could draw pictures if I had the time, but what determines the orientation is just how the gas was already moving.
Are dark matter and dark energy consumed by a black hole in the same way as normal matter and energy?
So if you had some dark matter that was moving toward the black hole, and if it crossed the event horizon, that would definitely not be able to come out again. Dark energy is a tricky thing because we don't know what dark energy is. We don't know if it's some kind of like energy field or if it's just a property of space itself. And so if it is some kind of energy field called a scalar field, which is something that we talk about in theory, then that could fall into a black hole. But if it's just a property of space-time, then it kind of, the question isn't quite the same. But dark matter definitely can fall into black holes. It's actually kind of hard for dark matter to fall into black holes because unlike regular matter, like if you take a bunch of regular matter and it's sort of orbiting around the black hole, it'll have collisions and it'll sort of heat up and it'll lose some of that rotational energy through collisions and then it'll fall in. But dark matter doesn't do that. So dark matter is weird because it can pass through itself and other matter. So it'll orbit much more stably. So it's harder to get dark matter to fall into black holes than it is to get regular matter to do that. It's a whole other topic, but. Yes.
I was wondering if there's a way to like measure the temperature of black holes because like it sucks in all energy. So is there like a certain temperature that like an average temperature or something?
Yeah, that's a great question. That is the question that led to the theorization of Hawking radiation, of the whole Hawking evaporation process. The idea that black holes should have a temperature. It comes down to questions about entropy, which is sort of a measure of like the disorder of stuff, and it's a long story, but yeah, we do expect a black hole to have a temperature that's associated with the sort of size of the black hole. For black holes of the size that we find in astrophysics, it's extremely cold in that sense. It just has to do with the evaporation. So really massive black holes are not really evaporating at any meaningful level, so they would be extremely cold. Really small black holes would be much hotter. But in general, all the black holes we know about are pulling in matter, so what we actually see is the regular matter around it, and that gets really hot because it's falling in. But the black hole itself does have a temperature associated with it if you leave it alone and let it evaporate. Otherwise, you can't really define it that way. But yeah, if you left it alone and let it evaporate, then yeah, it does have a temperature.
What would happen if two black holes of equal mass collided?
Yeah, so we've seen stuff sort of like that with the LIGO instrument. We've seen two black holes colliding. They haven't been exactly of equal mass as far as we can tell, but what happens when black holes of equal mass collide is that they create more massive black holes. So they merge together. I showed that little video earlier of these two black holes coming together. So those are black holes of sort of similar mass. This is a simulation of what that looks like. But basically, they come together and they make a bigger black hole with not quite the same as the sum of their masses. So let's say you have two black holes and each of them are 30 times as massive as the sun. Then when they come together, you would think that they'd have a mass of 60 times the sun, but they actually have a little bit less because some of the matter that made up the black hole, some of the sort of energy that made up that black hole sort of radiates away, sort of ripples away in space. And so what happens when two black holes collide is that they make a bigger black hole, but not quite as big as you might guess, because some of the energy sort of ripples off and goes away. The gravitational waves, yeah.
All right. Some more from the overflow room.
Okay.
I've got, did black holes have anything to do with the Big Bang?
Did black holes have anything to do with the Big Bang? So it's possible that little black holes were formed right after the Big Bang. Those are called primordial black holes, and this is another thing that Stephen Hawking kind of came up with. We don't have any evidence for those, but at the time of the Big Bang, the universe was very, very dense, and it could be that little pockets of high density collapse into black holes immediately, and they would be very, very low mass, very small black holes if those did form. But in terms of the sort of process of the Big Bang, there's a whole big long story about that. If you think of the Big Bang as like a singularity that then kind of expands to create the universe, there are some similarities between the way we think of a singularity in the Big Bang and the way we think of a singularity in a black hole, but they act very differently, and we don't know for sure that there ever was a singularity in the Big Bang. What we know about the Big Bang is that the universe was very hot and very dense at early times, and we think it went through a very rapid period of expansion in the first tiny, tiny fraction of a second, but we don't know for sure if there was ever a singularity at the beginning. And that's like a whole other talk, but I could go into that later if we want, but I think we're running out of time.
I want to get to a couple more from the overflow room.
Okay.
How can we increase the size of the virtual telescope lens? Is it satellites, or taking into account the Earth and solar system moving through space?
So one thing they want to do is just add more telescopes to get sort of a less fuzzy image. So if you have more and bigger telescopes, you can see a little better, even though the sort of total resolution is not necessarily increased. If you have space telescopes, in principle, then you can also combine the data from those. It's difficult, though, because you need to know exactly the position and the timing really, really well, and that's hard to do when you're not sort of stuck on the Earth. As for doing it sort of across orbital periods or whatever, I think also it's difficult there because of the necessity of getting the position and timing exactly right. But it may be that we'll figure out ways to do that. But the main thing that they want to do now with the Event Horizon Telescope is just bring more telescopes into the picture, and then just get sharper images.
What happens if stuff gets caught in the jets?
What happens in the jets? So the jets that come out of supermassive black holes are just these jets of extremely energetic particles, extremely hot radiation. So things can get kind of vaporized in those jets. Sometimes we've seen in distant galaxies that the jets can sort of blow bubbles in the matter around them, and you can create these sort of shock fronts where the jets run into the interstellar matter around them. And so there are some places where you see these sort of giant, they're called radiolobes, these sort of balloons where the jet has run into a bunch of other matter and starts radiating energy as it crashes into stuff. So they can do really dramatic things. So you don't want to get in the way.
So we've got about 5 more minutes of Q&A.
Okay.
There's a lot more hands going up than we've got time for. So I don't think I've ever done this at a science cafe, but we're going to do a lightning round.
Oh.
If I hand you a mic, you go.
Okay.
It's a question, not a story, okay, people? If I give you a mic, go. Starting over there.
Are black holes just a big ripple in space?
Are they just a big ripple in space? They're like they can create ripples in space when they move around, but they're sort of more of a dent in space, I guess, if that answers your question. Maybe. Yes?
How does Hawking radiation exist if nothing can come out of a black hole?
Okay, we're going to have to get into quantum field theory, which we don't have time for in a lightning round. But it has to do with sort of virtual particles that sort of pop in and out of existence in the space-time around a black hole. And there's a popular description that has like a virtual particle falls in and one escapes, and that's a complicated one that doesn't really work. It's really more about waves of energy with positive and negative frequencies. But it's quantum mechanics. I'm just going to say that. It's quantum mechanics.
Were the detection of gravitational waves the first proof of black holes? Then the images from M87 the first proof of what it does to light? Is that the big difference on those?
So proof is a tough concept. We've had extremely strong evidence of the existence of black holes for a really long time. I think that some of the strongest evidence has been this stuff about the supermassive black hole in the center of the galaxy. I would say that's the first really, really clinching evidence we had, seeing those stars go around and seeing how close they got to that object and knowing that nothing else could do that. But the gravitational waves gave us much more information about black holes and relativity, and this picture gives us a different kind of information. So we're just gathering more and more information about black holes. But I wouldn't say that any of these is like the final clinching thing. We're just learning more.
My question's about the existence of supermassive black holes and the formation of galaxies. A lot of galaxies seem to have supermassive black holes, and it might have had something to do with the creation of galaxies. My question is, has there been observed galaxies that do not have black holes in the center, and have there been observed supermassive black holes without a galaxy around them?
So as far as I know, every reasonably large galaxy we at least can't show that there isn't a black hole in the center. So I don't think we've ever found a supermassive black hole that's completely missing a black hole. And there's a pretty tight relationship between the mass of the black hole in the center of a galaxy and the mass of some component of the galaxy. So it does seem to be that they're correlated. They're pretty strongly correlated. They grow up together. We've seen a couple of galaxies that seem to have two supermassive black holes because they've had a merger with another galaxy recently. But I don't think we've ever seen a supermassive black hole outside the center of a galaxy. I think they really do kind of come together. But how exactly that happens is a big mystery in physics right now. How you make black holes and galaxies grow up together and have such a tight correlation in their masses.
What would the gravitational constant be at the event horizon, or can you even calculate that?
The gravitation, Newton's constant is Newton's constant everywhere, as far as we can tell, but the gravitational constant in the sense of like the gravitational acceleration.
Yeah, like not here, it's whatever, 9.81
meters per second squared.
Meters per second squared. Or that'd be really tricky because of like time basically stopping.
I've never thought about that question, so I'm not sure. But yeah, I don't know. I'd have to think about that. Okay. Exactly how you would define it in that sort of situation. Sorry.
Is there a way to determine if anything's behind a black hole given it's a hole?
So you can see the stuff that's behind the black hole because the light gets bent totally around it. So the black hole is a three-dimensional sphere, and if you put a black hole, you can't hide things behind black holes because the light that would be hidden just bends around. So black holes are impossible to hide things behind. They just also make a hole in your picture somewhere because they sort of, there's a direction where you can't see light in that direction because the stuff is being bent around, and then stuff that you should be seeing there is going into the black hole. But it doesn't really hide anything. It sort of just moves the light around in weird ways.
Let's give Katie Mack one more round of applause. Well, what'd you think? Was that fun? Yeah, I think so. And now we know that there's a whole other presentation about the end of the universe So you have to keep up with what's happening here at the museum for the next time Katie Mack's going to be at the Science Cafe to talk about the end of the universe. You should write a book about that. I think so. That would be cool. So there's a few giggles. Okay. Hey, don't forget, help us do some science here at the museum. The survey forms are being passed out right now. It shouldn't take but just a couple of minutes, 5 at most, for you to fill out the survey. That'll help us help you, because we want to make sure that we're giving you the best information and the best events that we can do here at the museum. Don't forget, we're here every Thursday night at 7 o'clock with topics from A to Z in all kinds of STEM disciplines. There's always something new and cool to learn here at the Science Cafe every Thursday, 7 o'clock. Next Thursday night, we'll be over in the WRAL 3D Theater for a documentary about the Neuse River with Bill Leslie from WRAL and a host of other experts on water quality from the Triangle. I hope that we'll see you all again real soon. Do us a favor, fill out the surveys. That helps us out a lot. Have a great night, everybody.